Hello, my name is Carl Reichert. I work at the Applied Research Lab here at Penn State University, and I'm on the faculty of the graduate program in acoustics. I'm also one of the heads of the Systems and Structures Health Management Technical Group, along with Dr. Cliff Lissenden. I'm going to describe for you a couple of additional projects that we're working on within the technical working group. Specifically, these are some projects that my colleagues and I are working on at the Applied Research Lab. While I'm just going to talk about two projects in particular, they're representative of a broad range of research that's ongoing at ARL. The first project is called Rapid Automation Technology Evaluation, Health Monitoring of Automated Drilling Systems, ADS. The goal of this project is to monitor the health and condition of automated machinery used in the manufacturing of aircraft. We're interested in this for two reasons. One, we want to be able to detect when the manufacturing equipment is degrading so that we can reduce the cost of operating that machinery and specifically reduce downtime and maintenance costs. In the case of manufacturing equipment, however, there's also a desire to ensure that the equipment is operating correctly and can maintain the correct tolerances in the parts that are being made. The sponsor for this project is the U.S. Navy Manufacturing Technology Program, also known as MANTech. The MANTech project pairs research organizations such as Penn State Applied Research Lab with manufacturers to improve the manufacturing processes and reduce costs for the systems that the military buys. The PIs for this project are Jeff Banks and Matt Rigdon at Penn State ARL. We also have a couple of CAV graduate students working on the program, Nick Carter and Trent Furlong, both with the graduate program in acoustics. The picture on the left of this slide shows robotic drilling systems used in the production of civilian aircraft. You can see that there is a robot on the inside and a robot on the outside that are working together to drill holes in the fuselage. In this case, the project is also trying to develop and field low-cost edge computing devices that can collect and process data, share that data in a shared data environment within the factory to help efficiently run the plant and manage maintenance practices. So our edge computing device is collecting current, vibration, and programmable logic controller data, performing anomaly detection and data analytics on the current sensor, vibration sensor, and PLC data, and providing a health assessment. That data, as I said, is pushed to a shared data environment that can be then combined with other data collected on other machinery and systems within the factory to then inform operations, maintenance decisions, and quality inspection. Now, we don't always have access to machinery that we're targeting for these kinds of projects. Specifically, we don't have full-time access to the aircraft manufacturing plant, for instance. So what we've done on this project is we've leveraged machine shops here at Penn State, and we've instrumented those milling machines in machine shops with similar sensors and using a similar edge computing device to collect the data. This slide shows the processing of raw motor current data that we're using to look at the health of both the motors in the motors in the milling machine, and also the drilling bits used in the cutting implements. One of the challenges in this project was the fact that the machine spends a lot of time in idle or in non-cutting activities. You can see in the graph up on the upper right, those sinusoidal lines are actually when the machine is moving the motors from place to place, and then the rapid or high frequency information in between those are where the actual drilling events are occurring. So one of the challenges with this project was separating out the actual drilling events from the gross motion of the machine so that that can be analyzed. In this particular case, we developed algorithms using statistical signal features and Hilbert spectrum analysis to feed machine learning algorithms that then produced an assessment of the motor health and the machine tool health. The idea being that we then take these algorithms and tools and we implement those in the field on the systems in the actual plant. A second project I'd like to talk to you about is one called Hybrid Prognostics at the Tactical Edge. This is a project with the Office of Naval Research and is more on the basic research side. The PIs for this project are myself and Jeff Banks. And one of the graduate students working on the project is Dan Watson, who's pursuing his PhD in the graduate program in acoustics. The idea of this project was to improve our ability to actually do prognostics, meaning we want to be able to predict the remaining useful life in an asset as it's operating in the field. This has been a challenge throughout time because we often don't have adequate data to give us a big picture of how the system is operating. And one of the goals of this project has been to collect data from various platforms, such as helicopters, patrol boats, and trucks or tactical wheeled vehicles, but also to collect data on maintenance actions performed, operational data, similar to the PLC data that we collected in the previous project from milling machines, and operational data, so logs from operators, to really get a context of how the system is operating, as well as the sensor data that we would be collecting. So in this case, we took the operational data and we were able to cluster it using machine learning into different stages of degradation. So you can see in the picture in the upper right, we have data clustered for health check of normal run with no fault data, overtemp conditions 1 week prior to a failure, overtemp conditions 1 week prior to another type of failure for a spur gear, and 1 week prior to a compressor failure. We time align these data with our maintenance records to understand when a problem was identified and corrected. And then we use our algorithms to track the progression of the system through different health states, from the no fault condition to the faulty condition, with the goal being providing early indications of failure as far out as possible so that we can take the system out of operation and perform maintenance at the time that's most opportune and not when the system is out on a mission. So we're currently working on 2 field tests involving training units. We're developing health monitoring equipment for patrol boats that see a lot of use with training units. And we're also autonomously collecting vehicle health data from ground vehicles. This has been another challenge in the health monitoring field, is actually getting data from operating systems when they're in the field. So we're really excited about these deployments of the systems because we'll be able to collect true operating data while the systems are in the field. And then we'll be able to establish a pipeline to populate data inventories that can then be used for applications such as machine learning. The last part of the project that I'd like to talk about is some work that Dan Watson's doing. And you'll see more about this in his poster presentation. But he's looking at scuffing wear in machinery, which is a particularly challenging problem because of the low signal noise ratio for the vibration measurements compared to what we get in a typical application such as gearbox health monitoring. So he's using a variety of sensors, both traditional lab grade and industrial grade accelerometers, as well as looking at new MEMS accelerometers in an attempt to reduce the cost of implementation. And we're also looking at using non-commensurate data from systems such as fluid monitoring systems that can look for degradation of lubricants and also particulate matter in those lubricants. You'll hear more about that in Dan's poster presentation. So those are just two examples of some projects that we're working on at the Applied Research Lab that fit within our technical working group here at the Center for Acoustics and Vibration. Please feel free to email or contact any of us within the group if you have any questions about any of the projects. We'd be happy to discuss them in more detail with you. Thank you, and enjoy this Center for Acoustics Vibration virtual conference for 2020.